director of Nordita, thorlacius+, to tell us a few words about Nordita.
So, thank you. And, well, dear conference participants, very happy on behalf of Nordita, the Nordic Institute of Physics, to welcome you all. And it is indeed an honor and a pleasure for us to co-sponsor the event of West, since, well, especially since Karl Heinz is a long-time collaborator and a frequent visitor at our institute. Now, I will not keep you long, but I do want to tell those of you who are not so familiar with Nordita a little bit about our history and what we are about. Now, Nordita is an institute for research in modern theoretical physics. It was founded in Copenhagen over 50 years ago, and for most of its history it has been owned and operated jointly by the 5 Nordic countries: Denmark, Finland, Iceland, Norway, and Sweden. And it was in fact decided to start the Nordic Institute to start a joint Nordic Institute to be located at the New Institute in Copenhagen. Shortly afterwards it became clear in the late 1940s that the theory division of CERN, which was originally located at the Institute, would be moving to Geneva, closer to the there. So that was the beginning of the Institute. It was originally called the Nordic Institute for Theoretical Atomic Physics. And that's the explanation for the A at the end of our acronym. But over the years, the scope of Nordita activities has widened and to include more or less all branches of theoretical physics. And it has widened to include new and emerging areas, while at the same time, I think the Institute has successfully maintained its focus on basic theoretical physics. And today, we have researchers who are engaged in both theoretical and computational research across a broad range of physics. This includes astrophysics, advanced matter physics, biological physics, statistical physics and complex systems, high energy physics, and gravitational theory, cosmology. Now, despite its small size, Nordita has played an important role in Nordic physics. Through the years, it has been important in building up and developing new and emerging areas in physics in the Nordic countries. I think maybe a very good example of this is the development and build-up of astrophysics in the Nordic countries in the 1970s, and then later complex systems and biological physics, which spearheaded also. And alongside this, it has also been a very important training center for theoretical physics in the Nordic countries. Basically, well, I think it's clear that a majority of all the senior faculty in theoretical physics at Nordic universities have been at Nordita at some point, either as postdoctoral fellows or as faculty, or as board members. So it has certainly been quite a large part of the history of theoretical physics in the last 50 years. Now, as a part of the organization of Nordic collaboration, Nordita was moved away from Copenhagen to Stockholm in 2007, and it is now owned by Stockholm University and the Royal Institute of Technology. But it remains very much a Nordic institute. It has gets much of its funding still comes jointly from the Nordic countries, and it has a Nordic board that decides how that funding is used, sets our overall policy, and decides on a lot of the hiring and recruitment. Now, we have a small academic staff, only about 10 faculty members, some of which are still based in Copenhagen. Now, in addition to the faculty, we have 10 to 12 postdoctoral fellowships at any given time. And this is all supported on our basic budget, but then based on additional grants that our faculty bring in, we have PhD students, postdocs, and long-term visitors supported. And the largest grant at the moment, by quite a stretch, is the 5-year ERC grant that was awarded to ISA some years ago, which currently supports an additional 10 or so people, so it is actually a third of the institute at the moment. We're of course extremely happy about having all this activity here. Now, in addition to the research of the in-house staff, we run various other activities. We run so-called scientific programs where a group of experts will come in, work together on a problem or in a particular area for maybe a month, 2 months. We also run workshops, summer schools, and we have a visitor program. Now the programs are perhaps our most important activity. We can accommodate about 20, 25 people at a time, and we run these programs basically, as I said, 4 or 6 weeks at a time. We run them for 8 to 9 months a year, so they're quite a big part of our operation. We invest about a third or so, between a quarter and a third of our resources in running these programs. Now they cover a wide range of theoretical physics and even beyond theoretical physics to sort of surrounding areas. You can in principle be on any subject in theoretical natural science, biology and neurosciences, for example. And in this way, I think we can provide an important service to a much larger scientific community than we could through our in-house research alone. The reason I'm going on about these programs is, of course, that these are completely open. Anybody can propose a program. You don't have to be working at a Nordic institute or anything like that. The programs that we eventually decide to run are decided by our board, following input from an external committee of experts. There's a deadline for submitting proposals each year in December. And then basically about this time we can inform people whether we're successful. So it's a fairly simple process. The proposals are relatively simple. And then if you are successful, what we will do is provide housing in Stockholm for the duration of the program for participants and a budget for travel and local expenses of various kinds. So I think I want to encourage you all to keep this in mind and keep us in mind when we make your plans. Now, I could go on and extol the virtues of Notita, but I think I will stop here. And let me again wish you all a very warm welcome and hope you enjoy a successful conference like this one. Thank you.
Thank you, Lars. And as a former postdoctoral fellow in Nordita, then located in Copenhagen, I could not agree more on what Lars said. Nordita really plays a great role in Nordic astrophysics. And next, I would like to invite Professor Eugene-Parker from the University of Chicago, who was already very nicely introduced by Axel and Paul Roberts, to talk about understanding the origin of astrophysical magnetic fields.
Thank you. Well, I read over the abstract that I wrote for the meeting, realized I had written it quite a while ago, so don't pay any attention to it. It was well meant. I'm going to think I will be focusing on the historical development. It's kind of interesting to see how ideas unfolded along the way. Things that we take for granted now were once unknown and then controversial, and now they're obvious to everybody, and that's the way science evolves. Magnetic fields were first discovered in China about 2,000 years ago. They were very practical. They made compass needles for navigation and for surveying. I read in a history book that the streets of old Beijing were lined up on magnetic north, not geographic north. And the historian, who obviously had no technical knowledge, wondered why in the world they didn't line it up with geographic north. It's easy to make a compass with which you can survey and indicate plot out directions in magnetic north. On the other hand, if you need geographic north, you need to sight on the pole star and then translate that into directions on the ground. And in those days, they simply didn't have instruments with which that would be easily done. A modern theodolite would have no trouble at all. In any case, it was widely used, and gradually this information diffused westward. I'm sure it was considered a trade secret among those who used magnetic compasses, so it did not become general knowledge, but by the year 1100, compasses showed up, magnetic compasses showed up in Europe. And the next big step was in 1600. William Gilbert in England got interested in the magnetic field of Earth as a whole. It was well known by that time, with ships sailing all around the world, that the magnetic field was everywhere. It was a Earth phenomenon, and he mapped out the field from a lodestone in his laboratory. Remember, magnetic iron oxide was the only source of magnetic field that they had, and he had a sort of globe, and he found it had a dipole field, and he did a lot of very precise geometrical measurements on the fields. In 1600, his book, The Magnet, came out, and it's a pleasure to read it. The geometrical things that he came up with, which we recognize as correct. He also had a very clear instinct about the nature of precise physical measurement and and how essential that was to understanding anything. And it's kind of fun to read the ridicule that he directs against some of his colleagues who didn't quite have that understanding. I guess we could use him here today sometimes too. He proposed that the Earth was, of course, a lodestone. That explained everything that was known. That there was a lot of magnetic iron oxide in it, and why not? In 1832, Carl Friedrich Gauss began setting up a worldwide network of magnetometers, and fortunately von Humboldt backed him so that they got things moving. And gradually, over the next 100 years, well, even up till today, the magnetometers provide quite a good network for mapping, not only mapping geographically, but watching the evolution in time of the magnetic field. And that's very important, as I'll mention later, when it comes to understanding the origin. In 1895, Pierre Curie, most famous for being the husband of Marie Curie, was doing experiments with ferromagnetic substances, iron and so forth, and discovered that above a few hundred degrees centigrade, things lose their magnetic properties. And of course, there went the theory for the origin of the cause of the magnetic field of Earth. The Earth is much hotter inside than a few hundred degrees centigrade. So one needed to begin thinking about what caused the field. In 1908, Hale detected and measured the 2 or 3 or 4 kilogauss fields of the sunspot umbra. So the sun became the other known magnetic body. And one somehow needed to understand that. In 1913, Hale, by overanalyzing his plates, found that estimated that the polar fields of the sun were about 50 Gauss. It was the only figure available for several decades, and you'll find in early literature that it's the quoted value. In 1947, Horace Babcock, measured long line of sight magnetic fields in other stars. This was the longitudinal Zeeman effect. And remember, if you can look at another star and see a net magnetic field, that star must have a very strong field and a well-organized field, because the longitudinal Zeeman effect is a quantity with a sign attached to it, And if you were to look at the sun, with all the fluctuations in the field, you'd find it was pretty nearly zero. So it was not only impressive, it was really astonishing that Babcock found other stars with fields of as little as 100 Gauss. It was apparently his threshold, up to a couple of thousand Gauss average. Now that must really be a magnetic star. I'm not sure to this day that all that is understood, but it indicated that magnetic fields are generally to be found in most stars, and as well as the planet Earth. The situation opened up even further when, about 1949, Hiltner reported on his work on the reddening of starlight. A distant star, the light coming through a dusty area, arrives reddened here at Earth and showing strong polarization. So somehow the dust grains must be aligned, and the magnetic field is the only way anyone could think of. Well, there were other ways, some inertial impact effects, but the only practical way of lining up the dust grains, and you had to worry about whether the dust grains were ferromagnetic or paramagnetic, and finally they're mostly paramagnetic apparently. And while you don't get an accurate figure for the magnetic field, unless you think you know accurately the composition of the grains, clearly we were talking about fields of a few microgauss. That means the galaxy has a magnetic field, stars have a magnetic field, planet Earth has a magnetic field, and we're beginning to get, by that time, the modern picture that wherever you look there are magnetic fields. Babcock and his son, both the elder and the younger Babcock, built a magnetometer that would scan the sun, and that was set in motion. They promptly found that the polar fields, which of course in the longitudinal Zeeman effect don't show up very well, must have been of the order of 10 Gauss, not 50 Gauss. And then people went back and looked at Hale's plates and found that he was pushing his luck a bit, and 5 or 10 Gauss is the modern estimate. And the question is then, what is the origin of the ubiquitous magnetic field? There was all kinds of speculation. The sun was certainly not made of magnetic material, and yet it was magnetized, so one could not appeal to the normal things like ferromagnetism. People wondered if there was some modification of Maxwell's equations or a modification of gravitational theory, and there was quite a lot of speculation. I'll mention only Blackett's ideas. They were probably the most elegant, and they survived for several years. He noticed that the ratio of the magnetic moment of Earth to the angular momentum of Earth and the ratio of the magnetic moment of the sun based on 50 Gauss and the angular momentum of the sun had the same value, which is surprising. There's really no similarity between the two bodies. And then when one of the first stellar measurements came in, 78 Virginus, he estimated the ratio of the magnetic moment to the angular momentum, and astonishingly got the same number. And then he thought a little further about this, and he started out with the Bohr magneton, which E over 2mc, and said, suppose we had a gravitational magneton where E is replaced by what we might call the gravitational mass, g to the 1/2 m, the G, capital G being the gravitational constant, and m the mass of the object, and then the angular momentum could be estimated from the rate of rotation of the star and what you knew about the radius of that class of star. It wasn't a precise measurement. And he found that that gave you the same value, namely something in the vicinity of 4 times 10 to the minus 14 centimeters per gram, square root of it. And it was one of these astonishing theories which theoreticians did not like because it was rather destructive of existing gravitational theory. But what can you do if somebody presents you with the facts? They forgot the admonition from Eddington, namely, never believe an observation for which you do not have a theory. But in any case, this seemed to provide a theory for these things. And then paleomagnetism came along, studies of paleomagnetism came along and showed that the magnetic field of Earth had reversed at some point in the past. And with the Babcock studies of the sun, it found that the field there reversed on the 11-year cycle of the sunspots. And then 78 Virginis began to vary and finally reversed with time. So this very elegant and somewhat astonishing theory was completely demolished. It was kind of fun while it lasted. Beautiful theories are so often brutally murdered by ugly facts. In 1919, Larmor looked at the spiral vortical patterns of some sunspots and concluded, not correctly it turned out, that they must represent some sort of a vortex motion. In fact, the spiraling is built into the magnetic field as it comes to the surface. But in any case, he suggested that the rotation induces currents which regenerates the magnetic field. And I never have understood what he had in mind. Maybe he didn't have anything in mind. It was almost as if he thought of convecting electrostatic charges or something. The induced effects simply don't have the right sign. And, well, let's see, I'll come to Cowling's theorem and then go back and pick up 1930. In 1934, we have Cowling's theorem, which has already been discussed today. And oh, thank you. And again, to repeat the point, this line follows the null points in this poloidal field with axial symmetry, and there's clearly a current flowing along this line because you can see the field circles around it, and yet since there's no field on this neutral point line, there's no way of inducing an electric field to drive that current. And you heard earlier there are some ways of beating this, not with steady state motions, but not with axial symmetry, but you can get around it. And I guess Cowling felt challenged by Larmor's idea to produce this theorem. I should digress for a moment. Well, let me complete it. In 1967, Paul Roberts showed that azimuthal flows cannot sustain a magnetic field. And axisymmetric flows can generate, and this is axisymmetric flows, not an axisymmetric field. Axisymmetric flows can generate a non-axisymmetric magnetic field. And these things are sometimes confused. People say it the other way around. So again, these things were greatly clarified. In 1930 and thereabouts, and I don't know who the author of this idea was, but somebody came up with the idea that suppose Earth has an electric charge, if not on its surface, maybe at some depth, but think of the Earth as an electric shell. You spin the shell, you get currents, and you get a dipole field if you have a uniform distribution of charge. And maybe that's the origin of Earth. Well, if you make even the most elementary calculation, you'll find that the idea is absurd. The charge is something like 10 to the 13 coulombs, which charges the Earth to something like 10 to the 17 volts relative to infinity. And I don't think we live in that environment at all. So that was just another passing idea. One should think of everything, of course, along the way, but then one should also be just a little bit critical quantitatively and so forth. This brings me to 1945, when Walter Elsasser published a milestone paper in the Physical Review in which he pointed out that the ideas being bandied about thermoelectric effect, piezoelectric effect, magnetostrictive effect, these atomic effects were all much too small to account for the magnetic field of Earth. And what's more, the idea that they would be stronger under pressure and temperature was wrong, and the opposite effect was expected. They would be weaker as things became more amorphous at high temperatures. And he said this leaves only the possibility of inducing the magnetic field of Earth with motions in the liquid iron core. This brought him to the subject of magnetohydrodynamics, and I've just sketched a couple of points here. You're all familiar with this. The electric field in the frame of reference of the fluid is essentially zero, neglecting the slight resistivity of the fluid. Therefore, the electric field in the laboratory frame of reference is minus V cross B over C, and of course you get the induction equation. There's some resistivity given to the diffusion term here. And I apologize for emphasizing this point in your presence because you're all very much aware of it, but outside the fields of dynamos and so forth, in aeronomy and in magnetospheric physics, there is a remarkable notion that the electric field is what's really driving everything, and that drives currents, which creates fields. The whole thing is twisted around and stood on its head. The electric field drives nothing. Here, the electric stress is equal to is second order in V over C compared to the magnetic stress. It is as negligible as time dilatation and Lorentz contraction. So, again, I apologize. You know all these things, but for the record, I thought I ought to say it. The idea was that the liquid iron nickel core, which has a solid core in the middle, but I won't spend any time talking about that. The electrical conductivity is of the order of 10 to the 16 per second. The magnetometers set up around the world, starting with Gauss, indicates a westward drift of about 0.18 degrees per year, which figures out to be a third of a millimeter per second at the surface of the core. So we know there's rotation, and what's more, you can see that it's a bit non-uniform. And the non-uniform rotation is driven by thermal convection. At one time, the favorite heat source to drive the convection was potassium-40. The geochemists insist that it never gets that it is not deep enough in the earth to drive it. And now the favorite idea is the heat of crystallization of the liquid core growing the solid core. I don't know any more about the details on that. I haven't tried to follow it. Back to Elsasser, he expanded B and V in tensorial harmonics, the modified Bessel function and Legendre, associated Legendre polynomials and so forth, and expanded both B and V in their own series. He showed immediately that the non-uniform rotation shears the poloidal field, which is, the poloidal field's about 5 Gauss in the center. And if you have non-uniform rotation, that stretches it out stretches out the poloidal field to provide a azimuthal field. And Bullard looked at the strength of the Coriolis forces and suggested that B phi might be as large as 100 Gauss. That would sort of equal the ultimate Coriolis force. It may not be that strong, of course. And then Elsasser and Bullard and Gelman and Takeuchi and Shimazu and Rikitaki and others, quite a few others, this is not an exhaustive list, went to work with the expansion of B and V. It turns out to be a very difficult problem, as many of you are aware. The series, for reasons that are not entirely clear, converges very slowly, which says, of course, that that particular reduction is not relevant to the physics that's going on, but nonetheless it's a mathematical procedure that we all understand, and they were unable to establish convergence. Bullard remarked once that if you use 8 terms in the series, it looks pretty good, and you compute the eigenvalue. They were doing this stationary case. And then you decide to check up on it by going to 15 terms, and the sign of the eigenvalue changes. So you know you're in deep trouble at that point. It was not until many years later that Gubbins and then Paul Roberts and Peck Harris finally established convergence of this scheme. And it, in my mind, raised the question of how to proceed. I had the good fortune to work with H.P. Robertson for a year when I was a student, and he used to emphasize that when the mathematics becomes too difficult, it is time to stop and think about the physics. Well, the mathematics, as far as I was concerned, was completely opaque, and this suggests two lines of inquiry. One is to think about the physics, consideration of the dynamo physics suggested by the long-term century, or almost 2-century-long observations of the geomagnetic field. And the other is to take a different route. Never mind fitting it into the Earth. Can you construct a simple, idealized scheme of fluid motion, kinematical fluid motion, that will regenerate field? And at least you can get round these dark speculations about anti-dynamo theorems that we're beginning to develop. As I mentioned here, the super-cowling theorem. This goes to Chandler's second theorem, of course, but I chose the non-mathematical procedure because I'm not that much of a mathematician anyway. And I got to looking at some of the figures of the plotting the geomagnetic field worldwide. They plot the various components, they plot the time variations and the rate of time variation and so forth. And it gives you a lot of patterns to look at. And when you look at those patterns, you realize there are upwellings in the core where there's roughly 10 identifiable regions around the world where there's clearly an updraft pushing up the field and then it's spreading off the surface. And the idea of convective cells is very suggestive that that's the kind of motion in the core. And then it occurred to me that the rapid spinning of Earth, remember the Earth spins once every 24 hours, and we're talking about the evolution of updrafts that last for hundreds of years. The Earth spins many, many times, so there must be powerful Coriolis forces. And that immediately suggests that each updraft is cyclonic. You have a converging flow at the base, and that gives you an upward bulge, and then the rotation of the Coriolis force rotates it around like that, and you realize you have just constructed a picture, which I've tried to reproduce here. Here's an azimuthal field line. You raise up a bulge and then rotate it, and you realize you're producing circulation of magnetic field in meridional planes, and that, of course, is the generation of the dipole field. This is not an axisymmetric configuration because of these loops. They completely violate the axisymmetric aspect of things. And each loop is conveniently described by an azimuthal vector potential. And if you now remember that this is the magnetic Reynolds numbers are not large here, and you diffuse these loops together, you simply get general circulation in the meridional planes, and I've sketched that in here. You can formulate this assuming that the mean field has rotational symmetry, which it does more or less. And the alpha over here, you can see, is equal to the filling factor. Well, let's suppose that most of the volume is filled with convecting cells, so we'll set that filling factor equal to 1. And then what remains is the rotational velocity of the individual convective cell, which you can estimate by waving your hands and appeal to dimensional analysis and so forth. And alpha represents the characteristic rotational velocity of close-packed cyclonic upwellings. In order to convert the individual convective cells into a mean contribution, I thought of it in terms of what I call what has been called the short sudden approximation, where in a very short time you imagine that your convective cell at high velocity charges up through the field, rotates it, whatever you would like. It doesn't have to be small. If it's small displacement, it can be a large displacement. And then you stop the system, hold the fluid stationary, and this is all on a small scale. The individual convective cells are assumed to be on a small scale, so you allow resistivity to wipe out, to diffuse the field, and you lose essentially all but the mean field. All the fluctuations due to the individual convective cells are on a much smaller scale. This is a two-scale concept, and then you repeat the cycle. It's not physically, it's not what happens, but it's a way of establishing clearly what the net effect is, and of course it shows, it gets around any possibility for an anti-dynamo theorem. If you combine these two equations here, and we'll move to Cartesian geometry now, just so I can display the kinds of things that you might reasonably expect. You get the two dynamo equations at the top of the page. You do the simple thing, consider a sine wave solution, and you get the dispersion relation that I've indicated there. If, for instance, you want a stationary dynamo, then you set this term equal to 0. This is the time rate of change. You see, this is the time rate of change. And you get a quartic in the wave numbers, and somewhere you get complex solutions and so forth. And what it amounts to is a propagating wave, which I've shown here, is bumped up against the geometry and cannot propagate, so it piles up against that, whatever is blocking, and this just the geometry. And you can have a stationary solution. On the other hand, you can have propagating solutions, as you see in the sun, with the migration of the field toward the equator. And the condition for getting dynamo effect is that the alpha times g is the overall fluid gradient, velocity gradient, has to exceed the dissipation. And well, that's all we need to say about it. That was in 1955. As already mentioned, in 1964, Brzezinski carried out a mathematical tour de force and showed, starting with an axially symmetric field, and then introducing as a small perturbation a non-axially symmetric field, and he carried it through. He gets the dynamo equations, which Sauer and Roberts pointed out in '76 seems to be particularly suitable for dynamical treatment of the fluid motion. Coming back to Brzezinski's original paper, I can say only that I prefer to read Sauer's paper, who deconstructed some of this, rephrased some of these things so that a mortal can begin to make some sense out of it. Brzezinski is quite a mathematician, and this was a really rigorous proof, I think, that you can have a dynamo, and there are no such things as anti-dynamo terms. In fact, over the years, it's become clear that almost all fluid motions, except for the nicely symmetric ones that we normally use in analytical work, almost all fluid motions have a powerful dynamo effect. And to continue on, in 1966, the next big step was Steenbeck, Krause, and Radler's famous paper in which they applied the quasi-linear approximation to developing the dynamo equations, and I just wrote it out here briefly. Again, you're all familiar with it, I'm sure. Break up the velocity into the mean plus the fluctuating part. This would presumably be the non-uniform rotation. This would be the cyclonic eddies, cyclonic convective cells, and do the same decomposition for the field into a mean field and the fluctuating fields associated with U prime. And this gives you the following equation. If you subtract, when you subtract the mean from this equation, you get this equation. And then you look at the second order terms here, and clearly if the perturbation, the U prime and the B prime are small, the second order terms are even smaller. There's also the point that's been made that the nonlinear terms fluctuate rapidly, and even though they may not be extremely small. Their cumulative effect is small because it oscillates and they cancel out. The importance of this formal procedure is that you can then proceed to give explicit expressions for alpha, which is essentially the correlation between the velocity and the vorticity, which of course is helicity, and it gives the turbulent diffusion in this particular form, which is, interestingly enough, the same diffusion coefficient you would expect for the diffusion of a scalar field. And the quasi-linear formulation fits naturally into the language of turbulence, where you talk in terms of these correlations. And I refer you to the monograph by Krause and Radler it's for an exposition on this. Somebody told me that the book is out of print and a bit scarce at the present time. And then I also heard that it was being reissued, which I think is a good thing to do. In 1979, I extended the short, I formally worked out the short sudden approximation and worked it out to all orders. And this C here is the Lagrange, this is the short sudden approximation, and the C is the Lagrangian displacement of the element of fluid. And you can remember in the short sudden approximation, you can have your convective cell rotate 63 times if it pleases you. That doesn't make C large because if you're just rotating in one area. So this is not limited to small perturbations. On the other hand, it has the limitation that you sit and wait with everything held fixed while the resistive diffusion spreads out the field, which is equivalent to saying a small magnetic Reynolds number. So you can explore large displacements, complicated displacements, but you can never get out of the small magnetic Reynolds number regime. With these higher order terms, say this one here, and these, this one is the most important, and this one, but you can reproduce Creighton's negative turbulent diffusion. You can get what I call the flux expulsion dynamo. If you want to generate a positive field, think of a way of deforming the field so that you reject and pump out of the region negative field. And the total result, of course, is a positive. So now let's look at the alternative, which is quite interesting. You can imagine ideal situations which may not have anything to do with nature, but they are mathematically tractable, and you can prove beyond any question that they generate field. I mentioned that in 1958, Backus, a rigorous formulation of the short sudden approximation and the alpha effect. Then there's the famous Herzenberg dynamo. Remember, this is two spheres spinning about inclined axes and embedded in a larger sphere with which they make electrical contact. And Lowes and Wilkinson set this up in the laboratory, and not without some difficulty, got it up to where it would actually generate field and vindicate completely, experimentally, the theoretical work that was done. Several people worked on the theory of this, and Paul Roberts was involved. Let's see, the Lortz dynamo, this one is the simplest mathematical solution. Gauletus treated two coaxial, counter-rotating vortex rings. Each rotating ring deforms the field, and that's fed to the other, much like Herzenberg's two counter-rotating spinning spheres. And Ponomarenko best illustrates the central role of helicity in generating magnetic field. He simply had a rigidly rotating cylinder of radius A, surrounded by a motionless conducting fluid with which it was in electrical contact. The cylinder rotates about its axis, so the fluid motions now have perfect axial symmetry, rotational symmetry. And he introduced a non-axisymmetric magnetic field. This is a little like the same flavor as the Brzezinski dynamo. Well, it's quite different mathematics. And he worked out the conditions under which mode, each mode M and K can be excited by sufficiently large Reynolds numbers. This provides an example of a magnetic field generated by axisymmetric motions. You remember I referred to Paul Roberts earlier. Let's see, I should mention that the dynamics of convective motions in a rotating sphere has been treated at some length by Buza. I believe they even did some laboratory experiments. Childress and Gilbert explored the stretch, twist, fold dynamo. Remember, suppose you have a loop of flux. You grab it firmly, you stretch it out, you rotate it so it's a figure 8, and then fold the figure 8 over, and you have double your flux. I think Albain was one of the first proponents of that particular mechanism, and you can see that you're amplifying the flux, and therefore it is a dynamo phenomenon. It turns out to be a very interesting subject when you get into doing the mathematics. Then I like very much the recent work of Paul Roberts and Gary Glatzmeyer. They were able to work out a code to cover both the dynamics of the convection and the magnetohydrodynamic effects on the magnetic field in a rotating sphere, thereby simulating the core of Earth, add heat at the center, and I guess they ate up a lot of computing time with this, but I think the result was worth it. They were driving the system fairly hard, just because of the math question of economics, keep their computing time down within limits. And they found an occasional field reversal this way. I don't know. I know you found one, Paul, but how many times did the system reverse? Anyway, I think that has been a real milestone. And that's about where we are today. The subject is huge. With all the diverse things that people have pursued, it's the amount of knowledge that is involved in the dynamo phenomenon is pretty much amazing. And it's been explored, and I'm looking forward to hearing about it at the rest of this meeting. But before I stop, I want to mention some obvious challenges that are not yet resolved and not often talked about. There are in several directions. I'm still concerned about the turbulent diffusion of strong magnetic fields in stars and galaxies where they're disturbed by convection, where the magnetic energy, magnetic stresses exceeds the hydrodynamic kinetic energy or Reynolds stresses, and the convection would seem to be limited to Albain modes, or the periodic motions. I've had some interesting discussions since I've been here, which I've enjoyed very much. One may be able to get around this somehow. Some of the formal mathematics seems to show that you get convection, that you get diffusion. But what I would like, from my point of view of always thinking about the simple physics, I cannot form a satisfactory picture in my own mind of how it is that you get this field to diffuse without tearing it apart a little bit. And, hopefully this will be clarified. Then the question is, the hydromagnetic equations, the magnetohydrodynamic equations are linear in B, and so the question arises way back at the beginning of the universe, what is the seed field that started it all? Because if I could declare that at time t equals 0, or some other time, there was absolutely no magnetic fields on a large scale in the universe, the question would be, how could they ever get started? If you use some of the thermal effects, the Biermann battery effect, several ideas, they're all weak, and you start out with fields typically 10 to the minus 18 Gauss. And if you want to build those up to, or maybe 10 to the minus 16, if you want to build those up to present day fields of, say, a microgauss, and if your characteristic amplification time, presumably these would grow exponentially, is, well, in a galaxy, 100 million years, you need an awful lot of times to get the thing up to present values. And that would say that halfway back to the beginning, the galaxy had a weak field. And in fact, when you look at distant galaxies, which are much younger, they must have been pretty much free of magnetic field, and yet the star formation and everything else in them looks just like what you're seeing in older galaxies. Somehow a galaxy has a magnetic field very early on in its evolution. And that brings us to the extragalactic fields, the intergalactic fields, which Phil Kronberg has been measuring using the Faraday rotation effect. And he finds fields of almost a microgauss extending between galactic clusters, distance of megaparsec through intergalactic space. And they cannot be generated by a dynamo because there just isn't enough time to turn that whole system over at once or twice or 3 times, which you'd have to do just to get started. There are some things going on there that are just outside the present understanding that is beyond magnetohydrodynamics. And then, let's see, this problem of diffusion of very strong fields may or may not apply to the sun, because even though you have an inventory of the field erupting through the surface, which comes to about 10 to the 24 maximums in one hemisphere over a period of a few years of sunspot maximum, that's so much field that unless the sun can recycle field, there must be 10 to the 24 Maxwells buried in the convective zone, and that gives you a mean azimuthal fields of a few thousand Gauss. Or maybe the sun is recycling fields by bringing up omega loops, and maybe it's only 300 Gauss. These are unanswered questions at the present time, and they're very difficult to come to grips with, because when you look at the surface of the sun, the fibril state of the magnetic fields, remember, the field looks like the fingers on my hand, where a finger would be 1500 Gauss with a radius of 100 kilometers. The space in between has apparently very little field, none detectable, and the mean field that you observe if you don't resolve this is simply a measure of the spacing of the 1500 Gauss fibrils. And that suggests that perhaps at depth in the sun, the field is in a fibril state. And then beyond that, things get so fuzzy. There's too many ifs. There's too many forks in the road that you don't quite know where to go. If you think about fibril fields, for a given amount of flux, they have much higher energy than just a continuous field. And we all know that nature, we think, tends to like to minimize energies. So it's a bit of an anomaly, but then you realize that if I had a continuous field in the sun, remember the convective zone of the sun is convecting because it's delivering a large flux of energy to the surface. And if I had a field that extended more or less uniformly through it, I would greatly impede that convective transport. And therefore things would heat up a bit farther down. And if you add the extra thermal energy to the extra magnetic energy of the fibrils and ask what state of fibril formation minimizes the total energy. Remember, a non-fibril state gives you a lot of thermal energy trapped way down because the convection is not so efficient. And if you have a strong fibril state, you've got extra magnetic energy, but then this allows the convection to move freely between the fibrils. You get, if you minimize this, you get numbers like 1 or 2 kilogauss for the field. All of which proves nothing because it does not tell me how this business of making fibrils comes about. So I have no means for determining whether I think there is fibril structure in the fields deep in the convective zone. I should add finally, the internal rotation of the sun is not understood. A lot of smart people have thought very hard about it and tried a variety of possibilities, and you always seem to end up with rotation where the angular velocity is constant on cylinders about the axis instead of the actual form of the sun, where the radiative zone is rigidly rotating and the convective zone, the angular velocity is more or less independent of depth, giving a sharp shear at the base. And then, of course, there's the question of the Maunder minimum. Various dynamo models show that the magnetic field of the sun can hiccup at times. And again, it's hard to focus on any one specific mechanism because there are so many possibilities. Well, I tell you these things so that you won't think we're working in a dead end by any means. We've got a long way to go, and it's fun all the way, and thank you for your attention.
Thank you very much for this very interesting. There are plenty of questions, and fortunately we have quite a lot of time. So, Igor?
Is it true that small parameter in short charge approximation is a small Stockholm margin? Or this approximation may be similar to the famous Krykov-Kazantsev model of vertical related time random velocity?
Well, it bears some resemblance. I think the answer to your question is that really it is, well, it does not compare with any of the others because it's not a perturbation on a realistic system. It's an unrealistic system where I don't have to worry about the diffusion during the deformation. I separate the deformation with a quick jerk like that, then I hold it while the diffusion goes on. And by not overlapping, you simplify the math in quite a different way from the way we usually go about it, where you may be limited to small fluctuations, and remember also it's equivalent to a small magnetic Reynolds number because you sit and wait for the diffusion to destroy all the small scale components. So I guess I think there's not much similarity there.
Quick question on what you said about intergalactic fields, because you mentioned that there should be something beyond magnetoaerodynamics, but this is something that is anyway subject to some decay in some sense, some diffusion. But we have the same problem in galaxies because younger galaxies show the same field, of the same order of magnitude.
Yeah.
So, but this is something beyond the magnetoaerodynamics. How could be not subject to diffusion, to decay? I mean, do you have an idea?
Well, first of all, diffusion on intergalactic scales, diffusion by any scheme we know of is just much too slow. I mean, it's slow enough on the scale of a galaxy. So I don't know that there's diffusion. People have talked about primordial fields, meaning that somehow it's an intrinsic property of the particle interactions in the Big Bang. But they all turn out to be on microscopic scales, which is no help whatever if you're thinking in terms of megaparsecs. So I just don't know. I really don't have a clue. It lies out. I suspect the explanation lies far outside magnetohydrodynamics, and I don't know what it would be.
Thanks.
You mentioned that turbulent diffusion of strong magnetic field, serious challenge for theory. What do you think about results of Günther Rüdiger and maybe our results? Because it's true that it's a difficult question, but if you've got almost homogeneous strong magnetic field, this challenge is not so, I think, difficult. What do you think about that? Strong magnetic field, but almost homogeneous.
I'm not sure I know what to think about it. I mean, it's...
It means that you've got strong magnetic field,
yeah,
but with weak inhomogeneity.
yeah.
So scale of homogeneity, huge, but field nevertheless very strong. I think in this situation it's possible to solve this problem.
I'm delighted to hear it.
I mean, are you talking about also the decay of sunspots, which...
Not decay of sunspots. I speak about, say, invention of turbulent diffusion. Of course, concept of turbulent diffusion should be, cooled down in presence of very strong and homogeneous magnetic field, because in strong and homogeneity, it's questionable what is magnetic diffusion at all, and gradient approximation. But if you've got strong magnetic field and almost homogeneous, I think in this case we can solve this puzzle, and we know answer. It's suppressed magnetic diffusion, and in presence of, say, convection, we find that it's suppressed for some minimal value, which not so, how to say...
Well, I have in mind a circumstance where the field is stronger than the convective velocities, so I'm not sure how the thing would work out, if it would work at all. I don't know. I have to think about it.
Organization. If you've got strong magnetic field almost homogeneous, you produce from turbulence more or less alveolic waves. And this alveolic wave, of course, is source of turbulent diffusion. But of course, if it's strong and homogeneous, it's another story. And of course, we cannot use concept of turbulent diffusion.
Yeah, I think one thing, perhaps I should not let it bother me, but whenever I start to think about one of these problems, I wonder if I should be thinking about it in some context of fibromagnetic field, where you have no magnetic field between the fibrils, and then you can do what you like, and this leaves the fibrils themselves more or less inviolate, but I've never been able to put it together in any reasonable, rational way. So
this issue of the fibril state of the field in the solar interior is very interesting, your energy minimization scheme for getting it. Can you get an estimate of the filling factor then of the magnetic field, and does it vary depending on whether you put this field in the convection zone or in the tachocline?
since I don't know how it is that the fibril state comes about, I really wouldn't know quite how to handle the problem. I don't know.
Just make a quick models of convection with magnetic field naturally give rise to these fibril structures. Isn't that the solution to the problem?
Well, certainly convection would give you a very inhomogeneous magnetic field, and you could probably see some fibril structure. But here the fibrils, at least at the surface, are much stronger. B squared over 8 pi is much greater than 1/2 rho v squared. So the field is really swept up and compressed into them. And the fibrils are not tangled the way you might expect, because they are so strong. They come up through the surface and maintain their integrity for some reasonable period of time. There may be exchange of flux between them. It's a subject that I think I would like to see people think hard about. I've thought hard about it and drawn a blank, except for the minimizing the energy, which says the fibril state is not implausible because somehow it minimizes the energy, but it doesn't tell you how it comes about. And it doesn't give any scales.
Lynn, I think I would be somewhat happier if you think of fibromagnetic fields as a segregation of magnetic fields, or segregation of the system into magnetized regions and less magnetized regions.
Yeah.
And I think that's actually really what you mean, isn't it?
Yes.
And then we would actually make contact also
Yeah.
with certain simulations. I'm thinking of simulations that Nigel Weiss has been doing together with Tau, Cataneo, and Brown John, I think.
Yeah.
In 98. So we should really think of regions which are magnetized and non-magnetized, and in the regions where the state is magnetized, it would still be there would still be large scale and small scale within that region, but so mean field theory should apply locally even in those regions. But in between, then there are regions over maybe some 30 megameters easily for the sun, if not even larger.
Well, see,
the field is relatively weak.
The separation of fibrils in the sun, depending on the total field strength, is anywhere from a couple of 100 kilometers to 1,000 or so kilometers. Let's see, if the diameter of the individual fibril is about 100 kilometers, if the separation is 1,000 kilometers, then the fibril occupies 1% of the area. And the mean field, if you looked at it, would be 15 Gauss, which is not untypical of quiet regions. So, yes, I mean, one thinks of these. What the structure within a fibril is, I don't know, though. There, the field completely overpowers any convective motions of which we know. So, well.
Okay, to keep up in the time schedule, let us thank Professor Parker again. And let us welcome the next speaker, Oliver Gressel from Queen Mary University of London. And Oliver is going to talk about the Redler effect in supernova-driven turbulence. So that, I guess, means the omega cross J effect or more differently.
Thank you for your introduction.
Should be all right.
It's right there. It's like that, yeah.
Thank you. I must admit I'm actually pretty awestruck by the previous speakers and the expert audience here at Nordita in Stockholm. And the more I'm really looking forward to be part of this vibrant institute in a year's time. And I must say it really feels great coming back to Stockholm. And I'm quite surprised that there's people who actually fight lawsuits to remain in London rather than come to Stockholm. So quite embarrassed to say that this is work that's now almost 2.5 years old, work that I've done for my PhD in Potsdam with the people whose names I've put up here. That's Udo Ziegler, who's written the Nirvana code, which is a general purpose MHD code that I used for my PhD, and that is to say I did numerical simulations, but I hope that at the end of my talk it will have become clear that we really rely on this beautiful formalism, which is the mean field magnetohydrodynamics, to understand what's happening in the simulations and why we see dynamos in some of them and why we don't see dynamos in others. And I must say I've learned a lot about the mean field concept and the alpha effect by Detlef Elsen and also by my supervisor Günther Rüdiger, who hopefully will join us on Thursday. I'm not sure about the latest version of the program. And the title is a tribute to Karl-Heinz Redler and to the occasion. And I can say that I actually detected the omega cross J effect in my simulation of the galactic dynamo and supernova-driven turbulence. So here's a brief outline. I'll briefly set it in the context of the magnetic fields we observe in dynamos. Then just briefly for the nomenclature I use, I'll introduce you to the concept of mean field MHD and the alpha effect. I'll present some simulation results, which include first directly driven dynamo that has been observed in simulations of kinetically forced turbulence in the galactic context, and then I'll show how we can understand this in terms of the alpha effect, and also the gamma effect and the delta effect, which all play an important role. And in the end, we'll see that it's really the whole full tensorial structure of these effects that's important. It's not just the alpha. So here we have a polarization map of a grand spiral galaxy. We see in the contours the polarized intensity, and we see, of course, the polarization vectors, which indicate a large-scale coherent magnetic field. And it has been argued how much is this a result from the primordial field. That's the field that just was there when the galaxy was formed, and maybe that's a strong hint that actually what gives you the seed field of galaxy formation. We have to think in terms of cosmology and structure formation, gravity, something that's usually neglected in the turbulence community where we think of kinematic driving, so we have to consider maybe gravitational fields to go to the origin. But then it becomes pretty clear if you look at these numbers. You estimate the turbulent velocity in the ISM to 10 kilometers per second, and that gives you a diffusion time of the order of 500 megayears maybe. And then you look at the differential rotation that winds up the field on timescales of maybe 250 million years. And so you would, in principle, think, okay, that's enough to create large-scale fields, but then that would be purely azimuthal fields where there's a clear indication of radial fields here in these maps. So the radial fields can only sustain against the diffusion by a dynamo mechanism. So the starting point for this work is to assume we actually have turbulence that creates a strong alpha effect in galaxies. So that brings me to what actually drives turbulence in the ISM. And you see here the nice picture of the Crab Nebula, which is a supernova remnant, and you see this filamentary structure and how it breaks up into turbulence and creates these 10 kilometers per second turbulent motion in the ISM. And there's also other players, but the supernovae are dominant by an order of magnitude compared to winds from massive stars, so that's why we focused on these supernovae explosions. And they're quite frequent. We have 2 or 3 of them in our own Milky Way, and that might not seem like a lot, but if you look at scales of gigayears, that's certainly several thousands to 10,000 explosions. And you'll see in the movies that I'll show from the simulation that it's really a very vigorous driving there. So I think I don't have to explain to any of you how actually you would amplify magnetic fields in a turbulent environment. It's really straightforward. You just need that cyclonic turbulence. You need the upwelling supernova bubbles to be spun up by the Coriolis force. The upper part of the bubble will move up, so that gives you a positive helicity, and there you go. And the main worry about the galactic dynamo actually was the turbulence might be too vigorous. So some people suggested that the galactic wind is so strong that it will disperse the magnetic field stronger than you can reinforce it by the alpha effect. Others actually said, wait, there's a strong density stratification, so the RMS velocity rises strongly with galactic height, and that would imply a downward diamagnetic pumping, the gamma effect. So some people argued you compress your fields in the midplane, and there you have them dissipated by the turbulence there. So it wasn't quite clear whether the driving might actually be too strong to maintain fields. And as you'll see, it's a really natural balance between the two effects, the wind blowing the fields away and the downward pumping. So we had the 2 pictures before. We had the large spiral pattern in the galaxy standing for the large scales, and we see here these little red dots. That's star formation. That's supernova, or let's take it as a picture for supernova explosion. So we have to bring these 2 scales together, and this is illustrated rather nicely in this visualization by Christoph Kissinger, who did simulations of global disks with a somewhat artificial forcing of the helicity on small scales. But these red bubbles, that's the supernova remnants, and this is a large-scale coherent field. And that's where the mean field formalism comes into play. So we want to encapsulate the effect of the supernovae and model the evolution on the large-scale field, and want to introduce the mean field formalism. And it was very successful in the 70s, models by Eugene Parker, and later by Andrei Shakurov and Dmitry Sokolov, to explain that this galactic field, the halo galactic field. However, it wasn't based on first principle. You would always have to make some back-of-the-envelope estimate of your alpha effect, of your sign of your alpha effect. Actually, there's a controversy about the alpha ZZ in the galactic disk, whether that is has got the same or different sign compared to the alpha phi. So what we attempt is to derive these closure parameters, and this is just to introduce my notation. I don't want to bore you here. To derive these closure parameters from direct simulations to see if you can base it on rigorous physics. So we all know that the alpha and the eta parameterize the turbulent EMF in terms of the mean fields. And here, in this case, I assume the simplified version where we only have vertical derivatives. So I'm interested in the vertical structure of the disk. And the interpretation of these parameters then becomes the well-known one of the alpha effect in the diagonal element of the alpha tensor, which feeds back the field and creates this exponential amplification. None less important is the antisymmetric off-diagonal elements, which comprise the gamma effect, the diamagnetic pumping. And we will see that in nice agreement with the quasi-linear prediction, this is in fact negative, so we have a downward pumping towards the midplane. That's something that, for example, the semi-analytic treatment by Katja Ferrier didn't predict, even though the situation was improved when she considered the stratification of the ISM. And then, of course, we have the well-known turbulent diffusivity as a diagonal element of the eta tensor. And last but not least, especially on this occasion, is the off-diagonal elements of the eta tensor, which are called the Redler effect, and which equally to the diagonal elements of this tensor, because there's an additional curl, couple the magnetic field back into itself. As we will see, here the alpha couples the B5 with the time evolution of the BR, and if you put that in here, you see you get the alpha square dynamo coupling the BR back into the BR. And similar to this, you can now, with the delta effect, couple the B5, the gradient in the B5, back to the time evolution of the BR, which gives you a similar feedback loop. However, it has been noted that because the delta effect is curled with the current, and the energy is actually the dot product with the current again, you cannot feed energy into the system via the delta effect. But you need an additional term, which is the Q omega, which is the shear term. So given you have the delta effect and shear, you can drive a dynamo if the sign is such that this gives you, together with the sign of the shear, a positive number. And then you can derive the dispersion relation, you find the critical wave number. And rather surprisingly, the dispersion relation, this is the growth rate, this is the real part, it's not the Reynolds number, versus the wave number, shows a very similar pattern than the classical alpha square dynamo, and the behavior that you get from this sort of delta square omega, or delta square shear, rather, delta square Q omega dynamo, is very similar, and you can indeed do mean field models of this. So